Dear students, in this video I will explain terminology used, spectral shift and solvent effect in UV visible spectroscopy. So let's start. Terminology used in UV visible spectroscopy. The first term used is chromophore. Any functional group which exhibit absorption of electromagnetic radiation in UV visible region is known as chromophore. Or more simply, one can say that any functional group which absorb UV visible radiation is known as chromophore. Not all organic molecule can show absorption of UV visible light. There are certain structural requirements for it. The molecule should have some specific structure and then only it can absorb UV visible light. This structural specificity is nothing but chromophore. Two types of chromophores are there. First type of chromophore is chromophore with pi electrons. That means unsaturated compound without heteroatom. The example is ethylene, carbon-carbon double bond, acetylene, carbon-carbon triple bond, propylene, again carbon-carbon double bond. Benzene is also a very strong chromophore in this category. Second type of chromophore is chromophore with pi and an electron. That means unsaturated compound with heteroatom. The example is carbonyl group, carboxylic acid group, ester functional groups, amido groups, nitro groups, etc. That means chromophore is a unsaturated functional group. And due to these unsaturated functional group, the molecule will absorb UV visible radiation. Second term used is auxochrome. It is a group which itself does not act as chromophore, but when attached to a chromophore, it shifts absorption maxima towards longer wavelength and increase intensity of absorption. The examples of auxochrome are hydroxyl group, amino group, ether group, primary, secondary amino group, etc. Now, according to this definition, these are the functional group which, if only these auxochromes are present in the molecule, the molecule will not absorb UV visible radiation. But if these auxochromes are present along with the chromophore, then due to these auxochrome, the absorption of that chromophore will increase as well as the lambda max will also increase. One example is there, benzene. Benzene, which is a very strong chromophore, benzene shows lambda max at 255 nanometer. And when to this benzene chromophore, auxochrome is attached like amino group, benzene converts into aniline, and now the aniline has lambda max at 280 nanometer. That means due to presence of amino functional group, the lambda max of benzene shift from 255 nanometer to 280 nanometer. This is effect of auxochrome. Now, why auxochrome increases lambda max? Why auxochrome shift the lambda max towards higher wavelength? Because all auxochrome have one or more non-bonding pair of electron. That means lone pair of electron, because each auxochrome has one heteroatom and each heteroatom has one or more lone pair of electron. Now this lone pair of electron extend conjugation. How this lone pair of electron extend conjugation? We'll see that. Now in this structure, the lone pair of electron is, in first structure, the lone pair of electron is with nitrogen and the double bond exists between carbon-carbon. But this structure is under resonance and the lone pair of electron is shared by the carbon. See in the second structure, the lone pair of electron is shared by the carbon and now the double bond is shifted in between carbon and nitrogen. That means at a given point, two double bonds exist in this structure. One is in between carbon-carbon and another is in between carbon-nitrogen. And this occurs due to sharing of lone pair of electron of that nitrogen. And that's why auxochrome increases conjugation. Conjugation means number of double bonds. As the conjugation increases, the lambda max will shift towards higher wavelength, lambda max will increase, as well as the absorption of UV visible radiation will also increase. This is the effect of auxochrome. One more example is given here. Auxochrome extends conjugation. How exactly? The one best example given here is carboxylic acidic functional group. In this functional group, carbonyl group is a chromophore, C double bond O is a chromophore, and hydroxylic group, OH group, is a auxochrome. And this is the structure of carboxylic group. Here the double bond exists between carbon oxygen of carbonyl group and the lone pair of electron is with oxygen of hydroxyl group. But this structure is also under resonance and the lone pair of electrons of hydroxyl group are shared by carbon. And now the double bond shifts in between carbon and oxygen of hydroxyl group. That means the double bond shift from carbonyl functional group to the hydroxyl functional group. It means that the unsaturation is increasing, conjugation is increasing, and as the conjugation is more, lambda max will shift towards higher wavelength. Now we'll see spectral shift or shift in the absorption maxima. The first shift is bathochromic shift or red shift. Absorption maxima shift towards longer wavelength because of presence of certain functional groups such as hydroxyl, amino group, or by changing solvent. Now bathochromic shift is also known as red shift because if you remember the wavelength of colors of visible light, the blue or indigo or violet color radiations are having shorter wavelength and the orange and red color radiations are having longer wavelength. And here in bathochromic shift, the absorption maxima is shifting towards longer wavelength, and that's why it is called as red shift. Here we'll take same example, that is benzene, whose lambda max is at 255 nanometer. But when amino group is attached to this benzene, it converts into aniline, and now aniline absorbs at 280 nanometer. That means due to attachment of amino group, the benzene's lambda max has shifted from 255 to 280 nanometer, and this is called as bathochromic shift. Bathochromic shift is also produced when two or more chromophores are present in conjugation in a molecule. For example, ethylene, its lambda max is 117 nanometer. And if we take 1,3-butadiene, where two ethylenes are attached with each other in conjugation, for 1,3-butadiene, the lambda max is at 217 nanometer. That means for one chromophore, for ethylene, single chromophore, lambda max at 170 nanometer. But when two ethylenes are attached with each other, the lambda max shift at 217 nanometer. This is bathochromic shift. Next shift is hypsochromic shift or blue shift. It is exactly opposite to the bathochromic shift. Absorption maxima shift towards shorter wavelength. That means towards the blue radiations, and that's why it is called as blue shift. This may be due to removal of conjugation or change in solvent. That means if we remove the conjugation, that means if we reduce the unsaturation, the blue shift will occur, hypsochromic shift will occur. Or if we change the solvent, hypsochromic shift will occur. We'll see the example of change in solvent. Now this is aniline. As we know, its lambda max is 280 nanometer. This 280 nanometer is in neutral medium. Aniline, when dissolved in neutral medium, its lambda max is 280 nanometer. But when aniline is dissolved in acidic medium, its lambda max shifts towards 200 nanometer. And the reason is that this is hypsochromic shift. For this, the reason is that the lone pair of nitrogen in acidic medium will produce hydrogen bond with the solvent. And now these lone pair of electrons are not free to increase the conjugation of benzene ring. And that's why hypsochromic shift occurs here. Reduction in the absorption maxima, hypsochromic shift. Next shift is hyperchromic effect. Increase in the intensity of absorption is known as hyperchromic effect. That means the amount of absorption is increasing here. It occurs due to introduction of auxochrome in the system. Fourth effect is hypochromic effect. Decrease in the intensity of absorption is known as hypochromic effect. It is exactly opposite to the hyperchromic effect. Hypochromic effect means reduction in the amount of absorption of UV visible light. It occurs due to presence of some functional group which can destroy geometry of the molecule. Now both these effects can be explained by diagrammatically. First we'll see hyperchromic effect. Here in this first diagram, the amount of UV visible light absorption is small, but when some auxochrome is attached, the amount of UV visible light absorption is increased. This is hyperchromic effect. Hypochromic effect is exactly opposite. The amount of UV visible light absorbed is more, but when some functional group is there which destroy the geometry of molecule, or if we remove the auxochrome, the amount of light absorbed will be less. This is hypochromic effect. Now in this diagram, all four effects are shown here. On x-axis there is wavelength. It starts from 180 nanometer up to the 800 nanometer. That means UV visible whole range is there. And on y-axis there is Emax. That means intensity of UV visible light absorption or amount of UV visible light absorption. And say this is a graph of a particular compound. Now bathochromic shift means if the lambda max increases towards higher wavelength. Hypsochromic shift if the lambda max decreases towards lower wavelength. Hyperchromic effect if the intensity of absorption increases. And hypochromic effect if the intensity of absorption decreases. So this diagram will explain all the four solvents used in UV visible spectroscopy. One should keep in mind that dry sample cannot be analyzed in UV visible spectroscopy. So a sample should be dissolved in some suitable solvent. There are certain criteria for selection of solvent. First criteria is it should not absorb in the region of investigation. That means solvent should not absorb in the region of UV visible spectroscopy. It should be transparent, and this is very important criteria. Solvent should be pure, it should be cheap, and one more criteria is solvent should not interact with the sample. These are few solvents which can be used in UV visible spectroscopy. First is water. Water whose lambda max is 205 nanometer. It can be used about 205 nanometer because below 205 or at 205 water itself will absorb the radiation. Above 205 it will be transparent. Same way acetonitrile, cyclohexane, diethyl ether, ethanol, hexane, methanol can be used above 210 nanometer. Other solvents are also there like tetrahydrofuran, dichloromethane, chloroform, carbon tetrachloride, etc. 95% ethanol is widely used solvent in UV visible spectroscopy. Now the thing is that lab grade ethanol cannot be used because lab grade ethanol may have benzene as impurity, and benzene show very strong absorbance of UV visible light. Effect of solvent on electronic transition. The position and the intensity of absorption maxima is shifted for a particular chromophore by changing polarity of solvent. That means a particular chromophore can be affected if we change the solvent. But for non-polar compound, this effect is not there because generally for non-polar compound, the lambda max remains same in polar as well as non-polar solvent. But for polar compound, the lambda max will drastically shift if we change the solvent, if we change the polarity of solvent. Alpha beta unsaturated carbonyl compounds will show two different shift. Now before that, what is alpha beta unsaturated carbonyl compounds? Alpha beta unsaturated carbonyl compounds are unsaturated aldehydes, unsaturated ketones, unsaturated carboxylic acids or esters. These compounds show two different effect on two different these compounds show two different effect on two different transitions. First transition is N2-pi antibonding transition. In this transition, the absorption band moves to shorter wavelength by increasing polarity of solvent. The reason is that ground state is more polar than the excited state, and the hydrogen bonding with the solvent is more in ground state than in the excited state. If this is the ground state, that is N non-bonding state, electrons have to jump to the pi antibonding state. In non-polar solvent, it requires energy delta E1 for this jump. But if we change the solvent from non-polar to polar, the ground state's energy will decrease drastically, because here the ground state N electrons will form hydrogen bond with the solvent, and now these hydrogen bonds will reduce the energy of ground state drastically, and now the ground state will appear with very low energy. But the excited state, that is pi antibonding state, is less polar, and that's why due to changing polarity of solvent, it will have less hydrogen bonding, and that's why the the antibonding pi state will reduce the energy little bit, not so drastic, and the electrons have to jump this much distance in the polar solvent. The energy required for this jump is delta E2. If we carefully observe, delta E1 is less than delta E2. That means in polar solvent, more energy is required for this jump. And as the energy required is more, the lambda max will be shorter, because there is inverse relationship between energy and wavelength. One example is there. Lambda max or absorption maxima of acetone in hexane is 279 nanometer. That means in non-polar solvent, the lambda max of acetone is 279 nanometer. But if we change the solvent, if we dissolve the acetone in water instead of hexane, water is more polar than hexane. If we dissolve acetone in water, its lambda max will shift towards 264 nanometer. That means from 279 to 264. This drastic shift is observed due to this changing polarity of solvent. Next transition is pi to pi antibonding transition. Now this transition shows exactly opposite effect than the previous one. In this transition, the absorption band moves towards longer wavelength by increasing polarity of solvent. The reason is that the dipole interaction with the solvent molecule lowers the energy of excited state more than the ground state. Now here the excited state is more polar than the ground state. If this is the ground state, pi bonding state, electrons have to jump to their pi antibonding excited state, and the energy required is delta E1 in non-polar solvent. But if we change the non-polar solvent to the polar one, if we select the polar solvent, the energy of excited state, that is pi antibonding state, decreases drastically, because in this transition the excited state is more polar. So the excited state's energy will decrease drastically. But the ground state's energy will not decrease so much, and it will have little bit lower energy than the non-polar solvent. Now in the polar solvent, electron has to jump this much distance, and the energy required for this jump is delta E2. If we carefully observe the energy difference for this particular transition, that is pi to pi antibonding transition, delta E1 is greater than delta E2, and as in polar solvent delta E2 less energy is required, that means more will be the wavelength, more will be the absorption maxima. So thus the value of absorption maxima in ethanol will be greater than observed in hexane. So this is the effect of solvent on electronic transition. I hope you understood all these concepts. Thank you very much for watching my video.